Hello, welcome. Today we're going to be learning about 5 essential Linux commands. The idea is that these are going to really speed up your life and make you feel a lot more in control of the work that you do. You'll quickly realize that the command line is actually super powerful, and a lot of the things that you maybe used to use programs for can just be done straight from the command line. So specifically today we're going to be talking about head, word counts, WC, grep, cut, and set. I'll also assume that you've done a little bit of command line stuff, so you know how to move around directories, you know that ls will list the contents of a directory, etc. Alright, let's start off with one of the more simple ones, head. Okay, so I'm in a directory which contains some Lumina reads. I can list the contents of this folder using ls, and I'm going to give the optional -l and h parameters so that it provides more information, so the output is actually human readable. There's a single fast queue which is pretty large, about 2.7 gigabytes. Now, I don't know about you, but I've definitely done this before. I'm going to use cat to print the fast queue to the console. And yeah, this happens. So I'm just going to clear this junk by typing clear. Of course, trying to print a 2.7 gigabyte file to the console isn't a good idea. Okay, so head is a perfect solution to this situation. Head will print the first 10 lines of a file by default. By typing head and then the file we want to print, we get a nice clean output of the first 10 lines. If we want to just print the first read, we can specify how many lines to print using the -n parameter. Faster files contain 4 lines per read, so if we want to print the first read, we can write head -n4 Illumina fast queue. If we wanted to print the first 2 reads, we can give -n8. Another practical use of this command is to subset a big file. Sometimes I just want a few hundred reads as a small sample when running programs so that they actually finish quickly. If we wanted the first 100 reads of this file, we can say head -n400, because there's 4 lines per read, so 400 100 reads. Now this would normally print to the console, but we can redirect the output into a file using an arrow like this. I'll call this file sample.fastq. So by doing this, we can see that we've created a new 100 read sample of our big fast queue. So we can see that that big Illumina fast queue is 2.7 gigabytes and the sample is 53 kilobytes. Just for a sanity check, we can print the first line of the big fast queue and the first line of the sample to see that they match. Word count's a really useful tool for counting things. It will print the number of lines, words, and bytes in a file. Here's a quick little demonstration. So I'm in the same directory as before, the one with Illumina reads. Let's look at the small sample fast queue. We can type wc, then sample.fastq to have a look. So reading from left to right, there are 400 lines, 800 words. That's using the space character to actually count what are words in the file. And the file is 53,000 bytes. So yeah, 53 kilobytes as we saw before. This is kind of nice to use because we can instantly see that there are 400 lines in this fast queue and therefore there's 100 reads. Let's do the same for the bigger fast queue. Okay, so it hasn't hung or anything. The WC program is running. It's just taking a while. Keep in mind that it has to look through 2.7 gigabytes worth of data to produce this result. Okay, it eventually finished. On the left, we can see there are roughly 20 million lines, so 5 million reads. That was a little slow, so we can do this instead. I'll give the -l parameter so that it only counts new lines and will ignore everything else. All right, there you go. It ran a lot faster. We can see that we got the same output as before as well. All right, let's do something a little more useful. I've swapped to a folder which contains a bunch of viral genomes. If I list the directory contents with ls, I just get this huge list of files. We can actually use wc here to make this better. We'll type ls as before, but then we'll pipe its output to another program, wc. Using a vertical bar, then wc, we can redirect the output of ls straight into wc. We're not writing a file or anything here, we're just directly streaming the output of ls into the input of wc. So running this, we get 2,881, but what is this? So remember that when we type in ls, it prints a line for each file in the folder. That way there's going to be as many lines as viral genomes. Piping this into WC, it then counts the number of lines. So the output 2881 is the number of viral genomes in the folder. The viral genomes all start with GCF, so I can give the asterisk wildcard, which will just match any file that starts with GCF. Doesn't matter what comes after. By checking that they all start with GCF, we can confirm that they're all viral genomes rather than other random files I might have just put in there for some reason. The purpose of grep is to print lines matching some pattern we give. This is super useful whenever you want to pull out certain bits of a file or just do a quick check of something specific you're looking for. I've swapped to a different folder again, sorry. A quick ls shows us that there's a single file, which is a SAM read alignment file. So these are human reads, which have been aligned to the human reference genome. Using WC, I'll just have a look at how many actual alignments there are in the SAM file. Okay, so there's 1.5 million alignments. I'll just show the first alignment so we can have a look at what we're dealing with. Looks like we've got an alignment to chromosome 1. Okay, so here's a question. This alignment is to chromosome 1, and let's say that's important to us, and we want to look at chromosome 1 alignments for some reason. How would you extract all the alignments to chromosome 1 from the SAM file? It's way too big to manually go through, so of course we have to use programs. So we can do that with grep really easily. Here we can just type in grep, then the thing we want to match, so this is, in this case, chromosome 1, CHR1, then the file. Okay, I should probably have seen that coming. There are lots of chromosome 1 alignments, and it was trying to dump all of them to the console. Let's just use the head command to look at the first 10 results of grep. There we go. So if you look at the third column, I know this is hard because the text wrapping, etc. But we can see they're all chromosome 1 alignments. Let's count how many results we get with WC. So there's almost 600,000 alignments to chromosome 1. So yeah, no wonder my console was taking a beating. If we do the same but search for chromosome 2 alignments, we can see there are 400,000. We can of course just redirect our results to a file if we want. I'm going to call this file chromosome 1 alignment SAM. So it's going to contain all those chromosome 1 alignments we found with grep and no alignments to other chromosomes. Let's have a look with ls. So it seems like it worked. Looking at the file size, it seems about right. I'll have a look at the first line to make sure. Okay, so grep can also be super useful by showing you the actual lines things are on. I've swapped to a folder with a VCF file, so a VCF file contains information about genetic variants. If I look at the top, there's a bunch of headlines which are super annoying sometimes. I'll show you where the actual variants start. Let's see, head ends 160, I think, variants. Okay, so this bit has lines of variants, but if I scroll up a bit, right, so there they are. There are headlines all the way down to like line 155 or something. Anyway, so I usually hate these for various reasons and would like a clean VCF with no headlines. Those headlines all start with ##, so we can find them with grep. If we also give the -n command to grep, grep will print out the line number of each match. So doing that, it looks like the last match was line 153. So we can kind of assume that lines 1 to 153 are all headers. Okay, so let's say you want to remove these lines. We can achieve this with grep. Grep has an optional parameter -v, which causes the opposite behavior to actually occur. So rather than printing lines which match our pattern, it will print lines which don't match our pattern. So if we want to remove those header lines, we can type grep, then -v this time, followed by the thing we're searching for, which is ##. So this is going to print all lines which don't contain ##. I'll just pipe that into head so we can look at the first 5 lines of the output. So what we can see is that those headlines are gone. To save this, again, we can redirect the output to a file, which I'm going to call vars noheader.vcf. With ls, we see the new file was created, and with head, we can see its contents is what we wanted. No more headlines. Okay, so now we're talking about cut. Cut lets you view files in a tabular way, so kind of like Excel, where everything is divided into columns and each line is a row. You can then select the specific columns you want to look at. So I'm still in the folder with that VCF file. I'll use tail, which is literally the opposite of head, to print the last few lines of the file. Okay, so the VCF format contains a bunch of information for each variant, but I don't always want that all. It's kind of cluttering up the console. So here we see the chromosome variants found, the position, which is 72,177, then the reference allele, that's like the canonical allele, and then the alternate allele, which is the variant, followed by the variant call quality. The rest I don't particularly care about right now, and it's just, again, cluttering up the console. So we can use cut to read this file because it's tab delimited, and just select the fields we want to look at. If I type in cut, then selecting the first field with -F1, I can look at just the actual chromosomes that the variants appear on. So we can just see it's printed out these chromosomes for each variant. If I go back and add field 2, it will also print out the position of the variant along that chromosome, because that's in the second spot. On the left of the screen, I've put the VCF format, so you can just see where each item is. If I want the chromosome position, ref allele, alternate alleles for the variant, and the quality score, I can type in cut -F12456. This is pretty nice because it's kind of like a little summary for each variant, and I can actually read it now. The rest of the junk isn't cluttering up the console. We can, of course, redirect the output to a file in case working with that summary format is just easier. I often would do the same thing for SAM files because they're also very cluttered. So if I just want the read ID, the alignment chromosome, position, and the mapping quality score, the MapQ score, I can get that with cut-F1345, so columns 1, 3, 4, and 5. All right, the last one for today is sed. Sed allows you to modify files line by line in different ways. The most common way I use sed is to delete lines or to edit or substitute lines of text to be in the format that I want. There's a lot of functionality that can be performed with sed. All right, so here I am back in the folder which contains a VCF of some variants. Before we used grep-v to remove the header lines, but we can also do this with sed. I'll just use grep again with -n to print line numbers for matches to remind us that there are 153 header lines. We can remove these lines very simply with sed. When using sed, you supply the lines you want to modify, then the operation you want to perform. So by typing sed, then 1,153, we can do stuff to lines 1 to 153. Specifically, the operation we want to perform is delete, so I will type in D. I'll just print the first 5 output lines with head. So we can see that the header lines on lines 1 to 153 have been deleted, and the output starts where the variants are. Let's just explore a little bit more what's happening. So this time I'm going to edit some lines rather than delete them. I'll type sed 1, 10, so we're going to be acting on lines 1 to 10. And this time I'll write S instead of D. This allows us to edit lines 1 to 10 rather than delete them. Of course, we also need to tell sed what we want to do to these lines that we're editing. We supply the target to modify, and then the actual substitution we want to make. This is split up by forward slashes. So here I can target ## and change it to ? So this command here will print out the file, but for lines 1 to 10, when it sees ##, it will change that to ? Let's just print out the first 10 lines of the output. So we can see that substitution was successful. All those hashes at the start of lines are now question marks. If I change the command to only edit the first 5 lines, it will be a bit more clear. The first 5 lines are being edited by sed from the hashes to question marks, and all the following lines are just going to be left as is and printed. Okay, now we're getting to the seriously powerful stuff. I've swapped back to the folder which contains a couple thousand viral genomes. Again, using ls and then piping this to wc, I'll count the lines, and we can see there are 2,881 lines, so 2,881 viral genomes. I'll print the first few lines using ls, then head to just have a look at what we're dealing with. Okay, so what I want to do here is for each viral genome, print out the names of its contigs. Let's have a look at what I mean by opening this first genome. This first line is a faster header, which means it's the name of the sequence that follows. Keep in mind that a genome is not always a single sequence or a single contig. For example, a perfect human genome would actually have 23 contigs, one for each chromosome. For viral genomes, we usually have one contig, but for some reasons, including if genuinely the genome has multiple separate genetic sequences, or if the genome assembly is not very good quality, it actually might be broken into a handful of contigs rather than a single complete sequence. Let's check how many contigs are in this genome assembly. I'll use grep to search for lines containing the arrow character. Keep in mind, only the faster headers will contain this character, so the thing we're looking for. Okay, so the only result is that first line. So yes, only a single contig in this genome. Other genomes might not be the same though. Let's search for faster headers in another random genome. All right, so this one also is a single contig. All right, this one isn't. Looks like there are 3 contigs. So what we're going to use sed for here is similar to what I just did, except in an automated way. So we're going to use sed to create a bash script, which will go into each genome and extract the faster headers using grep, kind of similar to what I just did. Let's go through this step by step. First step is to print each genome. A simple ls will do the trick. Next is to use sed to start modifying those genome names into something that itself resembles a command. I'm going to pipe the output of ls into sed, which will allow us to edit those lines, so those genome names. Here I'm going to tell sed that whenever it sees the start of a line, substitute that with grep and then the right arrow. To sed, the caret character here means the start of a line. Let's see what this does. Okay, so now it's actually looking something more like an actual command. For each viral genome, we've got some text which looks like basically a normal grep, which is searching for that arrow character. Okay, the second thing we need to do is to use head again, this time adding to the end of the line. So rather than printing to the console, we want to place the result of each grep into an actual file. So we'll use sed in substitute mode again, and we'll tell it every time it sees the end of a line, add the text arrow arrow contig names.txt. Again, here sed interprets the $symbol as the end of the line. I'm using a double arrow here to write the results to contig names.txt file instead of the usual single arrow, because double arrow allows you to append lines to a file. If we were to use the single arrow like before, the result of each grep would actually just override every other command, every other grep command, and write its results. So the same file would be created, written to, and destroyed 2,881 times. The double arrow, of course, doesn't actually have this behavior. It will just append to the end of that contig names.txt file. Okay, so we have our commands all laid out nicely. It's currently printing to the console, so let's actually send this text that we generated to a file. We'll call it script.sh. I'm just going to check the file real quick with head. All right, looking good. Looks like a bunch of commands all laid out. All right, only one thing left to do, which is run the script. Bash script.sh. And there you go, simple as that. Listing the folder contents, we see there are 2 new files. One is the script we created, and the other is the output file that we wanted to create. Hopefully it should contain all the contig names for each file genome. Let's have a quick look. Looking pretty good. The first genome is a single contig, it seems, but the second has 3. And it looks like the fourth genome has about 5 or maybe more than 5. I've only printed the first 10 lines. I'll just find out how many contig names that we extracted using this command. Okay, it looks like about 7,000. I'm just going to list the number of genomes in the folder. So again, we see that it's, well, it's actually 2,881 because of those 2 files we made. So there's almost 3,000 genomes, 7,000 contigs, so about 2 or 3 contigs per genome on average. I'll be making more of these videos, so feel free to subscribe if you want, and then the next time I make one, you'll be notified. All right, thanks, bye.